Dear students, today I want to share with you a new topic buffer solutions. Myself, Dr. Digna Varghese. Buffer solution is a solution consisting of a mixture of a weak acid and its conjugate base or vice versa. Buffer solution is also known as pH buffer or hydrogen ion buffer. Once again, I will tell you buffer solution is an aqueous solution consisting of a mixture of a weak acid and its conjugate base. Here you can see a weak acid and its conjugate base is shown here. That is, weak acid is acetic acid. Acetic acid in aqueous solution that acts as a buffer which consisting of a mixture of its conjugate base or vice versa. Okay. If it is a weak acid, its conjugate basis is strong base. If it is a weak base, its conjugating acid is a strong acid. Okay, so this type of conjugate acid base pair is known as buffer solution. So buffer solution is a aqueous solution of a mixture of a weak acid and its conjugate base or weak base and its conjugate acid. Solution. We can define buffer solution in another way. A buffer solution is one which resists any change in its pH even upon the addition of small amounts of acids or bases. You can see in the picture there is addition of a base to the buffer solution. If we measure the pH of this solution, there is no change. Okay, such type of solution is known as buffer solution. To the buffer solution, a small amount of acid is added, pH is measured, there is no change. Such solutions are known as buffer solutions. So, buffer solution is one which resists any change in its pH even upon the addition of small amount of acids or bases. Therefore, we can say that the pH remains unaltered upon the addition of a small amount of strong acid or strong base. Characteristics of buffer solution. It has a definite pH value. The pH remains unaltered by even on standing for a long time or on dilution. The pH remains unaltered upon the addition of a small amount of strong acid or a strong base. There are two types of buffer solutions. One is acidic buffer and the other one is basic buffer. Acidic buffer is prepared by mixing of a solutions of weak acid and its salt from a strong base in suitable proportions. You can see here an example, acetic acid and sodium acetate solutions. We know acetic acid is a weak acid and its strong salt is sodium acetate. This solution acts as a acidic buffer solution. It maintains the pH around 4.74. To this particular solution, we add extra amount of acetic acid or any other acid to this solution. It resists its pH. Okay. And basic buffer is that it is prepared by mixing of solutions of a weak base and its salt from a strong acid in suitable proportions. An example for this basic buffer is ammonium hydroxide and ammonium chloride. Mixture of ammonium hydroxide and ammonium chloride is a basic buffer. Ammonium hydroxide is a weak base. Its strong salt is ammonium chloride that is formed from the strong acid hydrochloric acid. It maintains the pH around 9.25. Okay, so basic buffer is a mixture of weak base and its strong salt from an acid. Acidic buffer is a mixture of weak acid and its salt from a strong base. Buffer action. The property by which the buffer solution resists any change in its pH even upon the addition of a small quantities of acids or bases to it is called buffer action. For example, if we take a buffer solution in a beaker, to this a strong base is added. If it is a basic buffer, there is no pH change by measuring. If we take acidic buffer solution in a beaker, to this a strong acid is added. There is no pH change. Such property of the buffer solution is known as buffer action. So, buffer action is the property of a buffer solution which resists any change in its pH even upon the addition of small quantities of acids or bases. Now we are going to study the mechanism of buffer action. Here we are discussing the buffer action of acidic buffer. We know acidic buffer is a mixture of weak acid and its salt from a strong base. Let us consider the buffer action of acetic acid and sodium acetate solutions. We know acetic acid is a weak acid, sodium acetate is its strong salt from strong base. So this is a acidic buffer. We know acetic acid is weakly ionized because it is a weak acid, whereas sodium acetate is completely ionized because it is a strong salt of acetic acid. So let us consider the buffer action of the acidic buffer. When we are adding acid to the acidic buffer, like a mixture of acetic acid and sodium acetate solutions, by the addition of acid, the acetate ion in the buffer solution forming acetic acid. On the other hand, acid addition of base to the acidic buffer solution, the acetic acid forms acetate ion. So, the pH is thereby maintained almost constant. Once again, I will tell you, please listen. The addition of an acid is countered by the acetate ion to form feebly ionized acetic acid. The addition of a base is countered by acetic acid to form acetate ion. The pH remains constant because by the addition of acid it forms acetic acid, that is a part of acidic buffer. By the addition of a base, the acetic acid reacts with a base to form acetate, that is also a part of acidic buffer. So the pH remains constant. That is about 4.74. Mechanism of buffer action. Here we are discussing the buffer action of basic buffer. We know basic buffer is a mixture of weak base and its salt from a strong acid. Here we are considering an example for a basic buffer, that is ammonium hydroxide and ammonium chloride solution. We know ammonium hydroxide is a weak base and it is weakly ionized. Ammonium chloride is a strong salt that is formed when ammonium hydroxide reacts with a strong acid like hydrochloric acid. Now we are considering the buffer action of basic buffer. When we add acid to the basic buffer solution, we know in basic buffer solution there is ammonium hydroxide that will react with hydronium ion from the acid. It will form ammonium ion and water. When we add base to the buffer solution, basic buffer solution, there is ammonium ion. Ammonium ion reacts with OH minus to form ammonium hydroxide. So the buffer action hence here can be explained by the fact that addition of an acid is countered by ammonium hydroxide and the addition of a base is countered by ammonium ion. If we add acid to the solution, basic buffer solution, its own ionized part is formed. When we add base to the basic buffer solution, in which the ammonium ion reacts with OH minus to form ammonium hydroxide, that is a weak base that is already present in the basic buffer part. So, by the addition of acid or a base to the mixture of ammonium hydroxide and ammonium chloride solution, so the pH is thus maintained fairly constant. That means the pH of the solution never altered. Henderson equation is used to calculate the pH of the buffer mixtures. Here we are considering the pH of acidic buffer. We know acidic buffer is a mixture of weak acid and its a strong salt. Here we are considering the weak acid as Ha in general representation and its highly dissociated salt is Ba. The ionization of the acid is represented as Ha plus water in equilibrium with hydronium ion plus A minus. The ionization constant is equal to concentration of hydronium ion into concentration of A minus divided by concentration of acid and concentration of water. We know the concentration of water is equal to 1. Therefore, the ionization constant of the acid is equal to Ka is equal to concentration of water into concentration of A minus divided by concentration of acid. Therefore, from this equation we can calculate the concentration of hydronium ion, that is equal to Ka into concentration of acid divided by concentration of A minus. In more general way, the hydronium ion concentration is equal to Ka into concentration of acid divided by concentration of salt. Taking logarithm on both sides, log hydronium ion is equal to log Ka plus log acid by salt. Taking negative on both the sides, negative logarithm H3O plus is equal to minus log Ka plus log acid by salt. We may also write in this way, minus log H3O plus is equal to minus log Ka plus log salt by acid. That is reciprocal of acid by salt. Here salt by acid. We know minus log H3O plus is equal to pH minus log Ka is equal to pKa. Therefore, pH is equal to pKa plus log salt by acid. This is known as Henderson equation or Henderson-Hasselbalch equation for an acidic buffer. Henderson equation is used here to calculate the pH of a basic buffer. We know basic buffer is a mixture of weak base and its strong salt. Here we are considering a general representation of a weak base BOH which is in equilibrium with B++ OH-. From this equation we can calculate the concentration of OH- is equal to Kb into concentration of BOH divided by concentration of B+. From this equation we can also written in the form concentration of OH- is equal to Kb into base by salt. Taking logarithm on both sides, log OH- is equal to log Kb plus log base by salt. The ionization constant Kb is equal to concentration of B plus into concentration of OH- divided by concentration of base. That is minus log OH- is equal to minus log Kb plus log salt by base. Here it is base by salt, minus of minus giving salt by base. POH is equal to pKb plus log salt by base. Therefore, we can calculate pH is equal to 14 minus POH. By using Henderson equation, we can calculate the pH of a acidic buffer or a basic buffer. Applications of Henderson equation. The calculation of the pH of a buffer solution prepared by mixing known quantities of a weak acid and its salt or a weak base and its salt. The calculation of the quantities of components that need be mixed in order to get a buffer solution of a definite pH. First one is the calculation of the pH of buffer solution prepared by mixing known amount of weak acid and its salt or weak base and its salt. Second application of Henderson equation is that the quantities of the components calculated that need be mixed in order to get a buffer solution of definite pH. That means if we want to prepare 4.74 pH of a buffer solution, then what is the quantities of the components to mix to get that particular pH? That can be calculated by using Henderson equation. Applications of buffer solution. In analytical chemistry, acetic acid sodium acetate buffer solutions are used for the elimination of phosphate radical in qualitative and quantitative analysis. Ammonium hydroxide and ammonium chloride buffer solution is used in the complexometric titrations using EDTA, used for maintaining constant pH in alcoholic fermentation. Tanning of leather. Tanning of leather means tanning is the process of treating skins and hides of animals to produce leather. Applications of buffer solution. Citric acid or sodium citrate, which is used for sterilizing penicillin preparation. Milk of magnesia. Milk of magnesia is used also known as magnesium hydroxide. If the pH value of a solution rises or falls too much, the effectiveness of the enzyme decreases in a process known as denaturation, which is usually irreversible. The majority of biological samples that are used in research are kept in buffer solution, often phosphate buffered saline solution (PBS). It's at pH 7.4. In industry, buffering agents are used in fermentation processes and in setting the correct conditions for dyes used in coloring fabrics. They are also used in chemical analysis and calibration of pH meters. In nature, there are many systems that use buffering for pH regulation. For example, the bicarbonate buffering system is used to regulate the pH of blood, and bicarbonate also acts as a buffer in the ocean. In ocean, atmospheric carbon dioxide dissolves in seawater and is hydrated to form carbonic acid. Carbonic acid is a divalent that it undergoes two deprotonation reactions to form bicarbonate and carbonate. The coexistence of these species in seawater creates a chemical buffer system, regulating the pH and carbon dioxide pressure of the oceans. Most of the inorganic carbon in the ocean exists as bicarbonate, with the concentration of carbonate ion and carbon dioxide comprising about 11% and 1% respectively. In biological systems, this is an essential condition for enzymes to function correctly. In human blood, a mixture of carbonic acid and bicarbonate is present in the plasma fraction. This constitutes the major mechanism for maintaining the pH of blood between 7.35 and 7.45.